Hello class and welcome back to this series on AP Computer Science Principles. I am Mr. Cunningham and today we are going to talk about binary, which is the number system that computers use, all zeros and ones. Now, before I do that, I want to do a quick review on the decimal system that you've been using your entire life, because I feel like if you truly understand the decimal system, then binary and later hex will both come a lot more easily to you if you realize they're the exact same system. Here's what I mean. Consider this number, 4,352. Now, when you look at this number, you do read it as 4,352 and not just 4352, and that is because of our decimal system. This 3, we understand, isn't actually a 3, right? The space that it's in changes its value. That 3 doesn't just represent 3, it represents 300. Because it is in the hundreds place. If you need a refresher on the base 10 system, I will go ahead and leave links to some of my videos in the description below. Please do check those out. When creating the number 4,352, what we're really doing is some complex multiplication and addition that we just take for granted. This 2 is in the ones place, so it's just 2 times 1. Makes sense so far. This 5 is in the tens place, which means every one of those digits is a group of 10, so that value is actually 5 times 10. Yes, I know my 5s look like S's, sorry about that. This 3 here is the hundreds place, so it's 3 times 10 twice. Times 10 to the second power, right? That is 100. 10 times 10 is 100. The thousands place, we could say, is 4 times 10 to the third power, right? 10 times 10 times 10 is 1,000. That is the thousands place. Yes, I see that I am sort of bouncing back and forth between little X's and dots for my multiplication. Sorry about that. So each of these places has a value, and the number you put in there is a multiple of that value. So essentially, every space you move to the left means you are multiplying your value by 10. Yeah? Tens, then hundreds, then thousands, then 10,000s, and onward. But why times 10? Why does it have to be 10 in each group? Well, the answer is it doesn't. The reason why we put things in groups of 10 is because we have 10 symbols for individual values, right? We have 0 through 9, and then once you get to 9, if you need to make a bigger number, well, now one character isn't going to do it for you, right? Once you get past 9, the next number you make has 2 digits. Right? The reason for that is we ran out of symbols, so we put them together into a group of 10 and move them left one spot. Because as I said before, moving left one spot means multiplying by 10. You may have heard of regrouping or borrowing when you're doing subtraction. This is like that, except in reverse. So what happens if you only have 2 characters? If you only have a 0 and a 1, can we still make very large numbers using only these 2 symbols? Well, yes, we can. Before I do any sort of lecturing or explaining, what I'd like to do right now is just count from 1 to like 8 in binary and see if you can pick out the pattern before I've said anything, okay? So, in binary, we've got 0, 1, there's 2, there's 3, there's 4, there's 5, 6, 7, 8, 9, and 10. Now, just looking at this chart, there are some patterns that jump out to me immediately. The moment we have all ones, the very next number has to be another digit in. I think in this case, digit is the wrong word. Digit, again, is a number that means base 10. So we're going to call these bits. Anytime I have all ones as I'm counting up, the next one is going to require another bit to make that bigger number. And that happened at 1, at 4, and at 8. Again, just something to notice for now as we begin to learn a little bit more about this, but these are your numbers from 1 to 10 in binary. And I used the exact same pattern, it's just that instead of counting all the way up to 9 and then moving to the next spot, I instead only counted up to 1 and then created a new bit. Here we are again looking at this place value system for decimals. Now, the only difference between decimals and binary is the number of symbols that we have available. Instead of 10, there are 2. So instead of each of these place values being worth another factor of 10, where it multiplies by 10 every time you go to the left, instead, because there are only 2 options for symbols, we multiply by 2 for every place value instead of by 10. Okay, so I've got here 1011. Okay? Now, the way that we can translate this back into base 10 is to do the exact same math that we already immediately do in our heads when we read a number like 4,375. It's just because we're not used to thinking in binary, it's going to require a few steps to get it back to base 10, which is more familiar to us. So let's take a look at this number. We've got a 1 in this 2 to the third spot, so I'll just say that is 1 times 2 to the third. There's a 0 in this 2 to the second spot, so I'll put a 0 in front of there, and we're going to be adding these together in the end. 2 to the first power times 1, and again, we're going to be adding these together. And then there is indeed a 1 in the ones place. So what is this number? Well, 1 times 2 to the third. 2 to the third is 2 times 2 is 4 times 2 is 8. So that is 8. Plus, well, this is 0 times 2 to the second, so that's just 0. 1 times 2 to the first, well, that's 2. And then 1 times 1 is 1. Our answer is 8, 9, 10, 11. In decimal. Now, I want to take a moment to emphasize the fact that there is nothing inherently good or bad about binary versus decimal. They are both very valid number systems. They both create the same math. We are just used to a base 10 system and have been taught in a base 10 system primarily because we have 10 fingers. That said, there are other cultures out there throughout history that have used non-base 10 systems for their math, and it worked out for them just fine. Okay, so as you can see, we've got 3 problems here that we're going to run through together. We are trying to convert these binary numbers into decimal. And the way we're going to do that, well, the way I do it is I set out some place value markers. And I do remember that technically there is a decimal point here, right? We could go off into fractions, but I think we'll do binary fractions in a different video. And just like with base 10 numbers, we start with the leftmost digit in the ones place. So that's going to go there, there. There's our 1, 0. Now all we have to do is remember what the value is of each of these places. And for me, having the first few powers of 2 memorized has been really helpful for me. We start with the ones place, and we double every time we go to the left. So this is the 2 place, the 4, the 8, and then the 16, 32, 64, and so on. As I said, memorizing the first 9 or 10 powers of 2 isn't entirely necessary, but it can be helpful, and I will go ahead and share that information with you at the end of this video. So, what is this number 1, 0? Well, we've got a 1 in the 2's place, and then we've got a 0 in the 1's place. 2 plus 0 is 2. So the number 10 in binary is equivalent to the number 2 in decimal. So here we've got 101. As before, we have taken the leftmost bit and put it in the 1's place, and everything else just sort of sits next to that. There's a 1 in the 4's place. I'm not even going to bother writing this 0. It seems kind of redundant to me, but I do see that there is a 1 in the 1's place. So our answer is 1 plus 4 equals 5. 101 in binary is the same as 5 in decimal. I hope this is making sense. As always, questions are welcomed down in the comments. Now here we have part C 1100, and I bet some of you out there have already figured out what it is and are ready to go. We've got a 1 in the 8's position. We've got a 1 in the 4 position, and then we have zeros in both the 2 and the 1 position. Our final result is 8 plus 4 is 12. So 1100 is the same thing as 12. So here's a question worth considering. If I only have 4 bits to work with, let's say I have a very small computer that can only handle 4 bits of information, what's the largest number I can make in binary? Well, in order to answer that, let's go ahead and go back to base 10 for just a second. If we are in base 10, our normal everyday number system, what is the biggest number I can make with 4 digits? Well, hopefully you said 9,999. Yeah? The way that you make the biggest number is to put the biggest symbol in every single one of the place values, as many place values as you have. What if, though, I only had 4 digits and I wanted to make a number like 11,000? Is that possible? Is it possible in our current number system to make that number with only 4 spaces? Well, no, it's not. I would not be able to make this number at all if I only have access to 4 digits. Yeah? The biggest number I can make is 9999, and the smallest number I can make is 0000. Right? 0 to 9999, that's the most I can go. I can't make 11,000. If I wanted to make 11,000, I would need another bit, or in this case, another digit, to be able to make that happen. If I have 5 digits, now, yes, I can make it. Put a 1 there, and I've made the number I'm looking for. So now let's jump back into binary. If I have 4 bits, what is the largest number I can make? Well, just like with the decimal system, the best way I can make the biggest number is to put the largest symbol in every space, right? Put a 1 everywhere, it's the biggest number I can make. Well, what does that make if I were to add those all together? 8 and 4 is 12, 13, 14, 15. Yeah? The biggest number I can make with 4 bits is the number 15. If I wanted to make the number 16, yeah? If I wanted to make the number 16, I would have to add another bit, and that bit is worth, and this is important, 16. Because we had made the largest possible number, 15, the next place value is going to be 1 higher than that. Okay, so now we've got 5 bits. 1, 2, 3, 4, 5. We've got 5 bits. What is the biggest number we can make now? Now, we already determined that 8 and 4 and 2 and 1 is 15. Yeah, we already got that. 16 plus 15 is 31. 31 is the absolute largest number that I can make with 5 bits using the binary system. So again, if I want to make a number that's bigger than 31, I have to make a place value worth 32. And notice how that is preserving the doubling every time, right? 8 times 2 is 16, times 2 is 32. So now here's my question to you. We've done this a couple of times. We now have 6 bits to work with. What do you think is the largest number that we can make in binary with 6 bits? And bonus if you can do it without having to do all the addition that we just did. There is an easier way. Okay, I think that's long enough of a pause. We know that the next place value over, yeah? The next place value over, well, we double every time, so it's going to be 64. Yeah? That place value is going to be 64, which means that the biggest number we can make without it, is 63. Okay, so now we're going to sort of put that into formula terms. As a reminder, we can rewrite all of these numbers into powers of 2. Now this 2 to the n that I just put here and the little dots I put in between means that n can be any number, right? We could go up to 2 to the as much as we need, just as we go with 10 to the as much as we need in the decimal system. So this number can go up as high as we need it to go. So let's say I've got a number that has, I don't know, 17 bits. And I want to know what's the biggest number I can make. Well, following the pattern that we talked about earlier, if we only have 17 bits to work with, the next biggest number that we're going to need is 2 to the 17th power. 2 to the 17th is going to be the next number that we need. Now, I don't know what 2 to the 17th is, but I know that whatever it is, if I subtract 1 from it, that'll be my biggest number. All right, Google tells me that 2 to the 17th is 131,072 minus 1 would be 1,000, or 131,071 is the biggest number we would be able to make. Once you have the pattern down, you don't need to do all the addition. You can use a calculator if you need to. Okay, one last thing before we end this video. Normally, I'm not a huge fan of just rote memorization, but there is no getting around the fact that having certain key ideas memorized can make things a lot faster and a lot easier, especially when you are in a timed situation such as the AP test. So, I have found that both in math and in life on occasion, it has been useful to me to be able to have the powers of 2 just stored away in my memory so that I can pull them out whenever I need to. And here they are. I recommend you write them down. I recommend that you make flashcards and really put some time into memorizing these. It will make your life a lot easier in the long run in this class. 2 to the 0 is 1. Anything other than 0 to the 0 power is 1. That's something for a different math class. Maybe I'll link a video below. 2 to the first power is 2. 2 squared is 4. 2 to the third is 8. Then 16, 32, 64, 128, 256, 512, and 1024. If you are a gamer or a computer nerd at all, you already knows a lot of these numbers because these are the numbers that computer specs tend to come in. You normally get things like 64 megabytes of RAM or something along those lines. It's almost always a power of 2 specifically because of the way binary works. If it's easier for you, you can just start at 2 and then double your way up until you're wherever you need to be. Like I said, memorization just saves you a little bit of time and a little bit of mental processing power. That's it for this video. We are going to be talking more about binary in the next few videos, and then of course we will be doing the Khan Academy assignment and continuing on through that. Thank you very much for watching. I'll see you next time.